to make this presentation. I'm going to cover two topics today, and we're going to have an introduction to the SPE Research and Development Technical section, also known as RDTS. And then I'll give, I'm an expert in drilling vibrations, and I'll give a distinguished lecture presentation called Tuning a Drilling Assembly Like a Violin. Which hopefully I'm making the analogy to BHAs acting like a musical instrument, and that should be a takeaway from this, is that we need to think holistically about how these tools are operating in the whole. So without further ado, just continue on.
Let me introduce, sir. So a very good evening and good morning to everyone who is present on here. So on behalf of IIT Guwahati SPE student chapter, I welcome all you today for these sessions under the Alpha series, that is Artificial Lift Production and Hydraulic Analytics Technical Series. And our topic today is tuning a drilling assembly like a violin. So we are delighted to have with us students, research scholars, faculty members, and industrial professions joining across from the country. Your presence truly reflects the growing interest in advanced topics within the petroleum and engineering. So about SPIT Guwahati these strives to create a dynamic platform for students by organizing technical lectures, workshops, and industrial interactions. Our goal is to bridge the gap between academic learnings and the real-world energy challenges. As a part of the vision, we have introduced the Alpha Technical Series, an initiative focused on delivering advanced industry-relevant insights in petroleum and energy engineering through the expert-led sessions. The series aims to expose students to core engineering concepts, real-world applications, and emerging technologies shaping the energy sector. So it's my great pleasure to introduce our distinguished speaker for the today's session. We are honored to have Dr. Jeffrey Bailey, Chair of SPE Research Development Technical Session, RDTS. Dr. Bailey retired as a Principal Drilling Mechanics Engineering at ExxonMobil, more than 32 years of work experience. And he has a PhD and Master's in Mechanical Engineering, along with a Master's in Technology and Policy from the MIT, and completed his undergrad from Stanford University. Dr. Bailey has developed more than 20 patents and authored several industry papers focusing on drilling vibrations, drill string redesign, and fracture mapping technologies. Today, we are privileged to have him share the insights on tuning a drilling assembly like a violin, where he will be discussing on how vibrations control and which also play a critical role in efficient and reliable drilling operations. So without any further delay, I would like to invite Dr. Bailey to begin the sessions. Thank you, sir. So, sir, you can start.
Okay, so let me start the technical presentation on tuning a drilling assembly like a violin. So I start with this brain tease. If you went to music concert and the musicians did not tune their instruments, how would the concert go? And I think we're all aware, that instruments, like before a symphony or a ballet or anything, there's about 15 or 20 minutes when all the instruments are being tuned. And, I kind of like the sound of all the tuning, but, without tuning, the symphony would not play very well. Even for rock concerts, it wouldn't go very well. So we recognize for musical instruments, they have to be tuned, but in the oil field, we don't have these requirements, and we can't even tell whether they're tuned or not. So, I mean, if you just look at these violins, you can't tell which one is tuned. If you look at pipe on a pipe rack, you can't tell when they screw it together what the vibration is going to be like. So, that's the basic problem, is that we're running bottom hole assemblies in the hole that are nowhere close to tuned quite a bit of the time. And that's what this technology is designed to do, is to identify for lateral vibrations, rotary speed sweet spots where we should be operating, or in many cases, how we need to change the design to have an assembly. We typically rotate somewhere between 50 and 200 RPM, kind of depends on the situation, but that's a fairly common range. But certain operations will be more like 50 to 60. Some operations will be like 140 to 160. So, we've got, a very good idea of what RPM we want to turn at once we get in the hole in most of our operations. And so this technology is to say, well, let's design an assembly that is optimized for operating at those conditions. So a violin or a stringed instrument basically has two nodes. It's the bridge down here, and then up here on the fingerboard is like where the finger's positioned. That determines the length of the string, and the length of the string with the tension determines the frequency. A bottomhole assembly is much more complicated because beam bending cannot be ignored. Here you're ignoring bending for the most part. It is described by a fourth order differential equation, which requires a little bit more complex mathematics. So we have two nodes here. Here we could have many nodes. This is an extremely badly performing bottom hole assembly. Talk about it a little bit later, but there are like 7 nodes in the first 100 feet. So it's heavily overstabilized. And believe it or not, the run before this, there was very bad vibrations, and it had one less. It had this roller reamer was missing, and we were having a lot of vibrations. So the team said, "Well, let's make it stiffer and put it in the hole and try again." And when they did, it got worse, much worse. So adding this node down here just increased the vibrations. We actually, for this in the model, we have to use a logarithmic scale to describe this BHA because the numbers are off the chart. So let's talk about nodal points. Certainly, you know, where the finger is being held up here on the fingerboard is determining the length of that string. So that's one nodal point, and this down here is a nodal point. And so if the fingers go closer to the bridge, the string gets shorter. And the frequency goes up. If away from the bridge, the string gets longer, frequency goes down. So we're changing, depending on the length, we're changing the frequency as we change the length. And that's basically what the mathematical model of, you know, any sort of lateral bending or vibrating system, be it a string instrument or a bottom hole assembly, works on those same principles, that you can adjust the frequency according to by changing the length. And so yeah, when I wrote this slide, I was thinking that lateral vibration was probably the least understood at the present time. I think we have a better understanding today of torsional and probably axial. A lateral is still an opportunity-rich environment. I think that's probably still true. There are challenges, and so back in 1992, when I worked early in my career working for Exxon, we had this bit walk test frame, and it's got a top drive up here, a bit down here, and you'll see it vibrating in a minute. But there were 2 collars, and this bit was pressing against a steel target. And this is where I got the original idea for this model. You'll see it vibrating in just a moment. But we had a bunch of stabilizers, and it was just lubricated with water. So basically you're seeing sine waves. You know, it's centralized and flexing in the middle. And it was to identify bit walk where the directional tendency goes to the left to the right from a platform back in the early 90s. Before there was a lot of rotary steerables, for instance. They'd already started to use bent sub motors, but it wasn't very common. It was still kind of early days of directional drilling. And so everyone did things according to stabilizer position for build drop. And we were trying to figure out what controls walk. And we didn't learn anything about bit walk control, but we did come up with a model that's a little bit different from others in the industry, because we were treating the bit as not as a nodal point, but as a source of excitation. So this demonstrates how we treat the bit. There is a lateral force applied to the bit, and it's just in plane dynamic bending. So all we're doing is pushing on the bit with a small force, and then seeing how the BHA responds. And this is called a force frequency response model. We calculate a vibration index, which is the bending strain energy of that mode of vibration. And then we compare that response to different BHA designs with the same amount of excitation and see what the difference in the response is in the model. So here you can see as we move this stabilizer here, we see a big deflection here and big deflection here. We're going to move this stabilizer down and look at the change in the modes. So we get it there into that position, and it's very quiet all through this interval here. We've dampened out the vibrations just by moving this contact to a different position. And that's what this technology is all about. This is a different chart, and here we've got the preferred position, and we're going to show that it's resistant to vibration at many operating speeds. We're going to start off slow and go faster and faster. You can see that it's going to be quiet all the way through here. See how it's very quiet all through here? Now it's going faster. So I'll talk about vibration indices in a moment, but we would say that with this position, we've got a wide operating speed, a low vibration index over a very wide range of RPMs. So that doesn't look like drilling, but this looks more like drilling. I've got a borehole. I've got two BHAs, one with long spacing and one with short spacing. And what this model shows is that the reactive force, which becomes a torque, between this middle stabilizer and the borehole increases significantly on the short space BHA than the long spacing. So having more flexibility and not being as rigid reduces the contact force at this node. Now, all these nodes have steel washers with a neoprene gasket that extends a little bit beyond the edge of the washer. So all these contacts are identical, and they have a little bit of grab against the borehole. And in these videos, you'll see the difference in motion as we turn the pipe. So it's enough contact that we're turning the ring here. Under the black light, you can see that the orange dots here are moving on this one. This one, you'll see it's rotating at the same speed, and I'm oscillating it back and forth a little bit to make sure it's not stuck, but this thing is hardly turning. And that is because this contact force is less than this contact force when it's rotating and vibrating. And that's exactly what we're trying to do is cause less dynamics under a similar vibrational rotational state. So then you start to think about the application of this model in the field, and you say, well, how can modeling help? I've got a drilling client and I've got a vendor, and many times the drilling client and the vendor are sitting in the same office, maybe, remote, it could be in another country, and they're working together. The tool's already designed by the vendor, right? So there are limited degrees of freedom, like how much can I change? Well, you have to think about stabilization constraints. There are tools that come with built-in stabilizers that you cannot move. There's magnetic effects to consider. If you have your MWD, you can't put it next to a steel collar. You may have to have a non-mag standoff. You have electrical power constraints. Some tools generate power and send power either uphole or downhole from there. So if you start to rearrange tools, you have to balance out the power consumption. So those are, constraints that give us, limited degrees of freedom. And then you have to ask the question, how complex is a model? Is it simple and repeatable? There are some models that take quite a bit of time. Time domain, a sort of integration can take hours to run, um, for each case. And so um, simplicity is definitely a benefit. Is the data available? Like sometimes there'd be a case where you don't have um, all the data you need for some of the complex models, but this model is very simple and doesn't require a lot of data. And can it be applied to every BHA? And then what is the right BHA design question? And the way we've framed this is, what is the best arrangement of components for my well and operating conditions? And so that's how we've applied this in the field. And we started doing this around 2010, and it's now done on almost every well that ExxonMobil drills. So what does the model consider? So this is a BHA design sheet. I don't know if any of you have seen these before, but it would have like a listing of the bit, the stabilizer, the collars, where's your MWD, where's your, various logging tools, LWD, and then where your drill collars, and then what does a BHA at the top look like? Parameter range, like what's your weight on bit range, what's your fluid density, although that has a fairly small impact on this particular model. What is the RPM range you're going to operate at here, 60 to 180? And then what is your weight on bit range? So just basic parameter range. And then the wellbore survey, which has actually quite little to do with this. It does affect the compressive loads and some of the elements, but it's a fairly small effect. So this is something that we know in advance on every well. Compare this, for instance, to a frac model where you need to know the stress at every depth. And if you know it at the wellbore, it doesn't mean you know it 100 feet from the well. So you get some complexity that's very hard to manage in some other modeling applications. This is about as simple as it gets. And there are absolutely no parameters to tune. There's nothing you can tune on this model. So for every RPM and weight and bit, we calculate the states. And this diagram illustrates two BHA designs. And we're looking at 30 RPM. This happened to be a turbine assembly, and we're operating about 30 RPM at surface. And you can see the difference between them is that they both got the turbine down here, and then there's a stabilizer in the blue one that's missing over here. Instead, the red one has a stabilizer about 75 feet from the bit, and this one has one at, say, 45 and about 95. So this has two stabilizers, this has one. And if we look at the calculated bending states in the beam bending model, we've got the red curve and the blue curve over here. And the little dots here are the nodal points. And so we've got the four states of the deflection, the first derivative, the second derivative, and the third derivative. The second derivative is a bending moment. So we calculate our vibration index by integrating the bending moment over the BHA and then comparing them. What's interesting is the change in the shear load at the contacts determines the amount of contact force at that location. So a higher contact, for instance, would probably have more wear, but it also is an indication of dysfunction because the wave that's traveling through the BHA is disrupted by the contact and requires, in this case, the blue BHA requires more force to keep the pipe within the borehole. So it has to make this constraint of lying within the borehole. And so these flat lines here are a measure of the amount of contact force at the stabilizer blade. And if you add up the red, it's much less than adding up the blues. So we have a lot more deflection, a lot more interaction of the blue assembly with the borehole, whereas the red one's just kind of wiggling, going down the middle and not interacting with the borehole so much. And we see that when we go to our vibration index. So again, the vibration index is the the bending strain energy integrated along the BHA at that rotary speed and at that weight. And here we've got our normalized vibration index. The values are normalized to something that just occurred in the field that looked good, but the values have not been changed for those normalization factors since like 1992. And there's been no tweaking of this model basically since 1992. It was really in the late 2000s, we started to put it into MATLAB first, and then it got implemented into the ExxonMobil drilling software. But the model hasn't changed. We just repackaged it. So there's a factor of 6 difference in the vibration index between these two BHAs at 30 RPM. And this is the process that we use again and again. And there's been like 2,500 studies now done using this model. It's being applied by the Bangalore Tech Center that ExxonMobil operates. And we started doing that, I don't know, maybe 6, 7, 8 years ago. I think the Bangalore Tech Center started using this model. So now I'm going to talk about some applications. So you build a model like that, and you don't know what's going to happen with it, right? You develop a technology, and you don't know to what extent it's going to be useful commercially. So or validated, right? There was no prior validation was determined for this by running it in the field and then developing a confidence in the results of what the model was telling us. It's not something that can be intrinsically proven. So let's talk about the case studies. So in this case, we had a high angle, like close to 90 degrees section, 12¼ being underreamed to 13½. So I don't know if many of you are familiar with the concept of an underreaming tool, but you certainly know that a bit has these cutter elements on it to open up a hole in the rock. An underreamer is a tool that's placed back from the bit some distance. In this case, it's probably about 100 feet. And it also has blades that extend when they pressure up on the tool and the blades come down. It extends and gives us a larger hole to cut as well. And it can be kind of a gnarly thing to work with. So there's a lot of concerns with making sure that underreamers are handled properly. And this particular vendor had never run actually with ExxonMobil before, and didn't really want to, they wanted to have a stabilizer right next to the underreamer and wanted to space out a little bit. So we got to, actually, this was kind of a compromise design for them. It wasn't what they preferred in the first place. But the drilling engineer insisted on running this optimized BHA in our modeling of the green BHA. And it had 30 feet between the closest stabilizer and the underreamer, whereas this was more like 10 feet. And the vibration index was very different. The red one has this big peak at about 125 RPM. We were operating about 140-ish. The green one comes up very much lower indices and is 40 times lower vibration index at 140 RPM. So we felt like this was going to be a good BHA to run. The vendor was very concerned, made the drilling engineer sign a waiver and so forth. But we ended up using the green assembly. And we had good results. The lateral vibrations were 2G or less, which is acceptable. That's considered low to very, very medium, quite low. Stick slip was less than 0.4, which is a good sticking ratio. It wasn't extremely hard rock. So these are good results for vibrations, very acceptable. And it turned out that our ROP, compared to ExxonMobil had taken over this platform from another company that had on 20-something wells, they had an average ROP of 13.5 meters an hour. And in this first run, we had 41 meters per hour. So, almost 3 times the ROP of the offset wells. Then there was another hole reaming while drilling example, and this came from Kurdistan. There were actually two hole sections. Because of some casing constraints, they had really hard time getting stabilizers next to the underreaming tools, so they were forced to put like two collars between. And literally the drill team, they knew about this technology and our desire to put more spacing, and they basically sent this BHA over and they said, how's this going to run? What does it look like in the model? And it looks very good. So we recommended that, no further changes. They just run it. And they basically had the longest and fastest hole enlargement while drilling recorded in Iraq at the time. This was around like 2013, 2014 timeframe. And they saved a bunch of rig time. So, if you're saving 12 days of rig time, it's, probably in the millions of dollars that you're saving. So it was definitely worthwhile to do this. And they actually had tried other BHAs and they couldn't even get them to bottom. And this BHA got to bottom and drilled very well in two different hole sections. This was one of the earliest examples of the VIBES technology. And this was a motorized BHA with in this red BHA, there was actually a stabilizer below the motor that was rotating with a bit. And in this blue BHA, we took out that additional contact and we took off the contact between the two collars and put it above two joints of heavyweight. And the operator had actually been doing this and wanted to say, well, what does the model predict for this case? And it turned out to be quite good. You can see that there's a big reduction, a factor of 6. They were operating about 110 RPM and had good performance. Over this 8-well program, they got a 36% average improvement in ROP. And the drilling engineer basically said, if I can keep the mechanical specific energy below 100 KSI going through these various formations, then he can make it to bottom in one trip without having to pull out and replace the bit. And you can see that the red BHA very consistently exceeded 100,000, which is the right edge of this chart, on a pretty regular basis, whereas the blue BHA only goes over 100,000 sporadically. And so we had good improvement in ROP, able to make it in single trips. And this is comparing from those two wells, the vibrations. This on this axis is the lateral vibrations, and this is the MSE. And we basically took most of the data to less than 2 G of vibrations and less than 50,000 on the MSE scale, which is very acceptable performance. You can drill a long interval with this sort of configuration. We talked about this turbine BHA before when I introduced the notion of vibration index. So this is the data from that. They had run 3 runs and had to pull out a hole multiple times. Unfortunately, we didn't have pictures of the stabilizer blades because they basically started to lose ROP in all these runs and pulled out of the hole. But what was interesting is that the bit grades were very, very low wear. This is a diamond impreg bit, so it actually drills by abrading the bit. And in order to drill, you have to wear the bit. It's the mechanism of drilling with that bit. When we went to the modified BHA that had lower vibration indices, the bits were coming out with quite a bit more wear, indicating that we're actually getting bit rock interaction in contact. And we had longer runs with higher ROP. This bar here is the average over that interval. And you can see quite a bit more contact of the bit in this case. So what I imagine was happening here is with all those additional forces acting the stabilizer, applied weight wasn't actually getting down to the bit. And that's why we weren't getting much weight to the bit and weren't able to drill as well. This is actually probably my single favorite example. They drilled one well with a red assembly that had a rotary steerable, a flex sub, and a flex sub is sometimes used for directional drilling when they want to allow a deviation in the hole. In this case, they were building to about 70 degrees. And then LWD, MWD, a stabilizer, and then compressive service drill pipe. The one change between these BHAs was removing this flex collar, and then the green BHA was used. And so if we calculate vibration indices, the red one was really optimized for about 120 RPM. The green one was optimized for 160, and we were actually drilling at 160 RPM. So we had this tuned correctly for the application. But we ran both of them and we had data. It turned out that, so if you look at the distance between here, this value is about 1 and this is about 0.3. So there's about a 3-to-1 ratio between these vibration indices calculated from the model. And this is the actual measured data. The average lateral vibration in this red BHA was 1.8 G, and in this green BHA, it was 0.6 G, and this is a 3-to-1 ratio. Now, this is a miracle. I can't say that, I've seen another case where there's a exact replication of the ratio of vibration indices to the ratio of vibrations measured from the data, because this is a very simple model. But this does confirm, that this model is giving us valuable information. And when we look at the detailed charts, for the red BHA, we see that there is quite a bit of dysfunction, higher lateral vibrations like 2 Gs, above 30,000 pounds weight on bit. And that flex sub was making it so we couldn't actually put as much weight on bit. But we did have a sweet spot at lower bit weights that agreed with the model. We've got, greens and blues in here. We've got red to the left, and we've got yellow and red and orange to the right. So we did sort of confirm our sweet spot for the red BHA, but it's all red across the top above 30,000 pounds. With the green BHA, we're able to go with low lateral vibrations all the way up to 50,000 pounds weight on bit. And we've got reds and oranges to the left and to the right. So we confirmed our sweet spot with the green BHA and our ability to run at much higher bit weight. So again, this is, I think, my #1 favorite example. I'll just cut this one short. Basically, if you start off with a BHA like this, and this does correspond to BHAs that I've seen in the field from different vendors, and you progressively make changes by simplifying the contacts and come down to this blue one, which has a rotary steerable, a stabilizer blade, a blade on MWD, and an LWD. And none of these tools are making contact with the borehole. In this case, you've got a lot of stabilization. There are vendors who make LWD tools that say, I have to have, like within 1/10 of an inch of the borehole, I have to have this measurement sonde, and it's going to affect my measurements. Well, if you're going to do that, do it in one place. And if you can do it twice, spread them out, is all I'm saying. But don't design them to go back to back like this and end up with these very high vibration indices that don't drill well, because drilling vibrations will be a limiter for this tool configuration. And we've got vendors that produce, BHAs of this entire range. And this entire example was designed to give the vendors the idea that when they go to design their tools, they need to consider it as an entire system and not just focus on, what's best for this individual tool. And I wish the message had gotten out more because we still see red BHAs like this, and we fight them in the field. So again, it's a very simple process. We basically take the BHA data sheet that's available for everyone that's running well. We need to know the details of the tool. We need to know the RPM in particular. If they have a motor, we can handle that. We just need to know the flow rate and the motor specs. and what weight and bit range. The hole inclination is not a big deal. And when they send a request, they need to know if it's like we're running a hole today and we need to know right now, or whether they're planning for 2 months from now. So that timing is also needed to do that analysis. And we've got several SPE papers that discuss this, and all this information has been made available to the industry. So what are the benefits? You know, increased drilling efficiency, more footage per day, lower MPT, you know, breaking less tools, fewer trips to change out tools, reduced risk, fewer days on the well is lower risk. And you sum all those up to get the total savings. So last week, I was at the SPE conference that was in Galveston, Texas. There was a very interesting paper. I haven't seen this data before, but this paper showed data from a well. I think they're doing MPD, managed pressure drilling, and they were measuring with a high frequency sub the pressure in the well, and they also had a downhole vibration sub. So in intervals where they saw very high vibrations, they saw very large fluctuations in the downhole pressure as well. And for an MPD operation, they're trying to keep it, you know, tightly between a couple of limits. And the spikes in the pressure were out of spec relative to when the vibrations were high. So very good and very interesting correlation between pressure variations downhole in an interval where they're trying to use managed pressure drilling, and high levels of vibration. So, you know, if we can get our vibrations down, we can also improve MPD operations where we have narrow margins. So, you know, I hope you understood the analogy with playing a stringed instrument, that we control the natural frequencies by the placement of the blades. And it's a very important design concept that, you know, still isn't being fully appreciated today by some of the people making the tools. I'll just kind of leave it at that. So I have questions. Also, this QR code will take you to the RDTS on LinkedIn. And again, if you are interested, please join RDTS if you're not already a member. And with that, I can take questions. I guess we're right at the 1 hour mark, aren't we?
Yeah, hello. So this is Rawat from WWT. I'm actually from the industry. If I may, I have a few questions.
Sure.
Yeah, so I'm from WWT International. I'm not sure if anyone is familiar with that. Its headquarters is in Houston. I'm based in Abu Dhabi. And we do have some tools that we make for drilling efficiency. So
Okay.
yeah, one of the tools we're looking at, it's not commercial yet, is about lateral vibration reduction. So this is quite an interesting subject for me. So
Is
my
that
first question,
sorry, Western Well Tool, is that WWT?
yes, correct.
Okay, thank you.
You might have met my colleagues in Houston or California.
Yeah.
Yeah. So my first question is about the model that you used with excitation to the bit.
Yes.
So usually the excitation, the bit, like yes, to actually model it, it's we excite the bit to see the vibrations right there. But usually the bit is under the reaction from the excitation from the top, correct? So has this been a challenge to create the model, and then you fine-tuned it, or it works just as accurately as applying the excitation from the other side and getting the reaction from the bit?
So what I'm doing is a force frequency response analysis. I'm applying an excitation at the bit, and it's the same for all different BHAs. I'm just assuming that there's a lot of people consider the bit to be a node. They say the lateral deflection is 0, and they put a pin there. I don't have a pin at the bit. I allow the bit to move laterally, but I push on it with a force. And then I see how that response propagates up the BHA. So it's a
Yeah.
force frequency response excitation with a lateral force at the bit. And different bits will give different lateral forces in the field. I'm just looking to see how sensitive the BHA is and how it responds to that excitation.
Yeah, so the point is not looking at what the bit is doing, it's how the BHA reacts to those vibrations, which leads to where to put the nodes of the BHA. So,
Yes.
and now my next question is a bit program-wise. So, can you give like the BHA design without the exact nodal areas to your design and say that we'll have like 3 stabilizers or 2, and ask the program with the given RPM, the RO, and the weight on bit to decide where the best locations are? Or do we have to do iterations of different BHAs and see exactly where the best performing, like we have, for example, 3 different possible BHAs we might use, and the program tells us, okay, use BHA number 3 because those spaced out nodes give the best? Or can the program, on the other hand, like you give it, okay, I have this BHA with this weight and this components, where should I place my stabilizers or nodes in general?
Yes. So just because of the nature of the problem, where if we have downhole tools, we're not at liberty to put them anywhere we want. There are discrete options that are available. We don't have a program that says, okay, just the best 3 places for nodes. It is really more specific to moving the blade from one component location to another.
Yeah, got it. And finally, and this is sorry, you're not done. Sorry.
Well, I will say that years ago, when we still had the MATLAB version, we did have an application in Western Colorado where they're using dumb iron assemblies. We could pretty much put the nodes anywhere we wanted, and we did have the capability to do that. It just didn't turn out to be that useful in the end because we are constrained operationally with what the vendor has.
Yeah, we cannot force the vendor to put it anywhere, just anywhere. We have to find the best option from the vendor's possibilities. Yeah, and finally, and this is more towards what we do. Can you assign in the current program, I'm sure future developments it will be able to be done, but in the current program, can you assign some elasticity and compressibility to a certain node? Because like what we're looking at is a stabilizer that's a bit elastic and absorbs shock, right? So on the program, can you assign currently, and is it a future capability, or it's not possible at all? These are like the 3 multiple choice answers to my question: elasticity and compressibility, and see how the bit with the BHA would react.
So the answer is no, we don't have elasticity at the nodes at this time. I would say one way to consider doing that is to say that probably as there's increased deflection, the blade would get stiffer. Is that correct? So it would be increasing stiffness with more deflection.
I would say that one of the stabilizer, what we're looking at, frankly, is based on a fluid bearing and some more elastic blades instead of the steel blades. So when the lateral vibration happens, it does absorb that shock, and the fluid bearing that's inside will be compressed a bit more, and instead of just solid to solid, it will be like a cushioning vibrational hit.
Right. So if I had to model that, I'd probably make that an undergauge stabilizer. And I'd say, well, if it's a 1/4 inch undergauge, maybe there's not much reaction for the first 1/4 inch. It wouldn't model the damping that your blade could provide in the system, but it would be softer. And then I'd see how that responds. That's probably how I'd approach it. The model doesn't have that capability.
Yeah. So yeah, maybe in the future such calculations can be added, but yeah, undergauge stabilizer for now makes a bit of sense. And I think that's all the questions oh yeah, final question. Most of the time at the operational RPMs and weight on bit, the more the nodes are spaced out, the better the results have been, or it's just the, it's independent.
It's definitely BHA specific. A lot of BHAs, when I first put in the model, will have a sweet spot at about 300 RPM, but we're operating at 120 to 140. So the first
Mhm.
thing I look for is what are the opportunities I have to increase spacing, to bring that curve down.
Mhm.
And that's what I start off usually the first time. That's my optimization, is to see what can I spread out a little bit, because uh, there is a thought in the industry, and I've had someone tell me you have to stabilize every connection, because if you stabilize a connection, it can't vibrate. And it's like, okay, um, that's totally opposite of, and somebody said to me some years ago, you're teaching exactly the opposite of what everyone else has been saying in the industry. So the idea that you have to space things out, to bring the natural frequency to the interval that you're operating, the rotary speed you're operating at, and tune it this way, is something that a lot of people didn't really have an appreciation for.
Yeah, understood. Thank you. I apologize for the several questions. I may
Oh
have a
no,
few more, but okay, then
thank you.
let me ask one more. Uh,
Okay.
about there's another study also. It's pretty common. I'm not sure who runs it the most, but about the BHA harmonics, like the harmonics or resonance, like the RPMs that should be avoided to avoid the amplifying vibrations at those. Obviously, the change of nodes will change that frequency, like it will change the RPM. But is it integrated in that program also, or it's they run independently?
Um, that would be independent. Yeah, that'd be separate.
All right.
That I typically is associated, I believe, with models that consider the bit to be pinned. I think I've seen that more. Um,
Mhm.
I've never tried to harmonize the two approaches, because I've felt like we had a very good approach, and I didn't have access to other models, to be honest. You have to pay license fees and whatnot. I know some of the models you're probably talking about, um, but I mean, it's a good question, is how those critical speeds interact with our sweet spots, and I have not studied that.
All right. Thank you for the input. I hope everyone also benefited from my questions.
Thank
And
you.
thanks again for the full presentation.
Yeah, thank you.
Hello, sir.
Yes.
Sir, as a student, I have a question like how a student or how SP can help us to get a job. Like as a student, we always need a job. So how SP can help us to get a job?
Well, there are industry events that bring people from the industry together with students. I'm I think people from the industry visit student chapters for presentations and whatnot, and get to learn the. I mean, it's an excellent question. Um, I haven't
Like
really
how
been.
should we approach like in just directly mail or just through a LinkedIn or anything? How should we approach as a student?
Right. I would really like to have Khalid Enab respond to that. If you could send me an email, I can forward it on to Khalid, and maybe he has a better answer, a more thorough answer. Um,
Sure, sure,
my
sure.
my my basic thought is, strive to do research and gain knowledge in areas of interest that you learn that the industry is interested in from SPE. A lot of the things that companies are working on are very closely related to topics that SPE is addressing. You talk about digital AI, you've got the themes, the grand
Yes, sir.
challenges. These are the things that the companies are caring about and that they're looking to do work on in the future. So if you develop skills that are aligned with these technologies, then you should be in a good position to get a job. And then SP does give you the ability to get into contact at various events with people in the industry. So.